Alright guys, welcome to this page of the notes, and what we're going to do on this page is we have a few additional things we need to say about complex solutions or imaginary solutions to polynomials. And it's simply this. If you go back and look at the two example problems that we just did for Descartes' rule, if you take a look at the column where we listed all possible combinations for imaginary or complex solutions, what you should notice is that every single number in those columns is an even number. And here's what that means. What that means is that a polynomial will never, ever have an odd number of complex solutions or imaginary solutions. Simply saying it's not possible to get just one imaginary solution for a polynomial, right? They must come in pairs. They have to be an even number of imaginary solutions. And again, you can go back and look at the two example problems we did for Descartes' rule, and you'll see exactly that. In that imaginary solutions column, every number in there is an even number. All right? There are no odd numbers. You can't get an odd number of imaginary solutions for a polynomial. It's just not possible. But even further than that, it actually turns out that imaginary solutions for polynomials, imaginary or complex solutions for polynomials, must come as complex conjugates. Now, that term should sound familiar. We talked about complex conjugates back in chapter 4 when we were talking about imaginary solutions to quadratics. We talked about this idea of a complex conjugate, which is simply this. Complex conjugates are complex numbers where the imaginary part of the number is just opposite in sign. Let me give you a couple of real quick examples. You may remember some of these. If you have 2 plus 3i, the complex conjugate is 2 minus 3i, right? Those are complex conjugates because the imaginary part of the number is just opposite in sign. If you were given 5 plus I, the complex conjugate is 5 minus I, right? You just change the sign of the imaginary part of the number. One more. If I gave you negative 4i, the complex conjugate would be plus 4i. So hopefully what you'll remember from back in chapter 4, that discussion on complex conjugates, the complex conjugate is just the opposite sign for the imaginary part of the complex number. So here's what we're telling you in this section. Not only can you not get an odd number of imaginary zeros for a polynomial, but actually imaginary zeros must show up as complex conjugates. They have to. So here's the idea. This is the conjugate roots. Let me highlight it for you, and then I'll show you in a couple of example problems. If a polynomial has real coefficients, the complex roots, if you get imaginary solutions, they must occur as complex conjugates. They have to. Which is why it's only possible to get an even number of imaginary roots. Complex conjugates means that there's 2 of them. There's a positive and a negative version, right? So there's no way you could possibly get an odd number of imaginary solutions if they must appear as complex conjugates. So let's go and do a couple of example problems and we'll show you how this is going to work. Let's factor this first guy to find our zeros. X squared plus 4 equals 0. We'll go ahead and subtract that 4 to the other side, which means that x squared is equal to a negative 4. Take the square root of both sides, plus or minus the square root of a negative 4. I know I'm going to pull the negative square root of 1 out, and I'm going to get imaginary. The square root of 4, of course, is 2, so I wind up with plus 2i and minus 2i as my zeros, and right there you see an example of imaginary solutions or complex solutions showing up as conjugate pairs. Plus 2i, minus 2i. Those are complex conjugates. All right, let's do another one. It looks like if I take a look at this guy, the first thing I recognize is I have a GCF. I can pull an x out of all of those. So let's go ahead and pull an x out of all of those. That leaves me with an x squared minus x minus 6 is equal to 0. That's interesting. Actually, it looks like I believe I can factor this into two binomials. The easy bit, x times x, gets me x squared. The trickier bit, I need two numbers that multiply to a -6 and sum to a -1, which would actually be a -3 and a +2. And so I apologize. Again, you're watching live math. I haven't worked this out before. I'm not entirely sure why I put this problem in here, because I'm not going to get imaginary solutions, but it's worth the practice anyway. The more factoring you can do, the better. We'll use the zero product property to split this guy up. I get x equals 0. I get x equals 3. And I get x equals a -2. I don't even get imaginary solutions, but it is good for factoring, and it further emphasizes the point. Fundamental theorem of algebra tells me I should get 3 zeros, and I do 1, 2, 3. It's just none of them happen to be imaginary. So again, not really sure why that one made it in here, but it's worth the extra practice. Let's try this one. This one looks a little bit more promising. Actually, this one looks to me like a difference of squares. I believe that I can rewrite this as an x squared squared minus 256 can be rewritten as I believe 16. Let me double check that on a calculator. I'm pretty sure it's 16. 16 times 16, 256. Awesome. So I'm going to rewrite this as 16 squared. Now, because this fits the difference of squares formula, I know that I can rewrite this guy as two binomials that are a minus b and a plus b. So that's going to be an x squared minus 16 and an x squared plus 16 is all equal to 0. But then you should recognize this as yet another difference of squares. I can rewrite this first guy right here in green as another difference of squares. I can rewrite that as an x squared minus a 4 squared, right? So that's that little bit right there in green. I still have this guy though, x squared plus 16, which I can't do anything to that. But since this is a difference of squares, let's factor it into its two binomials, which would be x minus 4 and x plus 4. And then I still got that little bit right there, x squared plus 16. Okay, now, zero product property is going to let me split these guys up. So let me slide up a little bit here so I've got space for you to see. X minus 4 is equal to 0, x plus 4 is equal to 0, and x squared plus 16 is equal to 0. This is going to come out to be x equals 4. This is going to be x equals -4. So there's two of my zeros. And then this one, x squared is equal to a -16. Awesome, there they are. So I'm going to be taking a square root of a negative number. I know I'm going to get imaginary solutions. Let's check to see if we get complex conjugates. Plus or minus the square root of a -16, which of course is going to come out to be plus or minus. Square root of 16 is 4, and then I'll have I. And so absolutely, x equals 4i, x equals minus 4i, and I do. I get those complex conjugates. Imaginary complex solutions must show up as complex conjugates. This was a 4th degree polynomial, so I should wind up with 4 zeros, and I do. Plus 4 minus 4, and then plus 4i and minus 4i. So the idea here is this. If you have imaginary or complex solutions, they must come in an even amount, and they must be complex conjugates. Head on over to the next page of the notes and we'll take a look at how this is going to apply to a different kind of problem where I ask you to give me the polynomial. So I'll meet you over there.